Now, since we're talking about moving around particles and chaos, then we've got a temperature issue here, right? We've got some considerations to think about in terms of temperature. So take, for example, liquid water going to gaseous water. That's boiling. We're boiling water molecules, okay? The system would be just the water molecules. Well, they're going from liquid to solid, or liquid to gas, rather. So delta S for the system was positive, right? It's becoming more chaotic, an increase in number of positions for those water molecules to occupy. Now, the change in entropy of the surroundings is going to be determined mostly by whether or not heat is flowing into or out of the system here. Okay, vaporization is endothermic. Okay? That means that you have to put heat into the system in order for the vaporization to happen. Well, if you're putting heat into the system, where is that heat coming from? It's coming from the surroundings. So heat is leaving the surroundings. The surroundings are becoming less energetic. And if they're becoming less energetic, that should decrease the motion of the particles of the surrounding. It should get slower, or less movement. Well, that means that the heat of entropy of surroundings should be negative, right? The surroundings should actually be becoming more ordered as the system becomes less ordered. So the problem is, well, is that a spontaneous position or not? Well, it depends on the size of delta S of the system and the size of delta S of the surroundings. So that when I add them together, if I get a positive value, it is spontaneous. If I get a negative value, then it's not. Then the reverse process is spontaneous. Well, in terms of water boiling, we know that is very temperature dependent. It's a spontaneous process if the temperature is high enough. But if the temperature is too low, then water doesn't spontaneously boil. Okay, so we need to understand what's happening with temperature here. All right, so if you have a situation like that, where the entropy of the system and the entropy of the surroundings have different signs, then it's the temperature that's going to determine the overall entropy change of the universe. Okay, so for the vaporization of water, we know that if the temperature is above 100 degrees Celsius, then delta S of the universe is positive, and if it's below, then it's negative. At lower temperatures, heat transfer has a greater effect on this than at higher temperatures. So how do we determine the entropy of surroundings? The sign of the entropy of surroundings depends on the direction of heat flow. Usually, if it's an exothermic reaction, the system is an exothermic reaction. That means that heat is being given off of the system into the surroundings. The surroundings are taking on that heat. They should be becoming less ordered. So for exothermic reactions, delta S has a positive sign. It's the opposite of delta H because of the way the heat's flowing, and negative for endothermic reactions. The size of the entropy of surroundings depends on how much temperature change there is and what temperature we're at. So we know that at constant temperature, heat flow is represented by delta H. Okay? So at high temperatures, the heat flow is not very much at very high temperatures. But as you decrease the temperature, the amount of heat flow can change. So there's an inverse relationship between entropy of surroundings and temperature. And so we can represent that by delta S surroundings is equal to negative delta H reaction over T, the temperature. All right? So this is some sort of a summary of delta S of the system and surroundings and universe and what's actually going on. So if the delta S of the system is positive, in other words, the system is becoming more disordered and the surroundings are also becoming more disordered, then the whole universe is becoming more disordered. That's definitely a spontaneous process. If the system and surroundings are both becoming less disordered or more ordered, then so is the universe. And that means that the reverse reaction is spontaneous. Well, what if they're in opposition? So if the system is becoming more disordered, but the surroundings are becoming more ordered, or vice versa, we can't really tell what delta S of the universe is unless we know the magnitude of those two. And that's going to be dependent on temperature, as we saw. Okay, so here we have some process, whatever it is. Delta H is plus 22 kilojoules, and delta S is minus 13 joules per Kelvin. Okay, by the way, entropy is measured in joules per mole Kelvin or joules per Kelvin. Okay, so we want to know at what temperature does this process become spontaneous? What do we know? Well, we know that delta S is saying that it's becoming more ordered because it is a negative sign. And delta H says that it's an endothermic process because it's absorbing energy. So those are in opposition as far as what's going on here, okay? So if, by the way, if you see delta S without a little subscript written, it just means we're talking about the system, not the surroundings, okay? So in order for this to be a spontaneous process, the overall entropy change of the universe has to be greater than 0. And we know that that means that the entropy change of the system and the entropy change of the surrounding has to be greater than 0. Well, the entropy change of the system is already negative 13 joules per Kelvin. So the only way this is going to be positive is if the entropy change of the surroundings is positive and greater than 13 joules per Kelvin. Because then we'll end up with a positive value for delta S of the universe. Okay? So this is really nothing more than just solving an inequality. Delta S system plus delta S surroundings must be greater than 0. We already have an expression for delta S surroundings, negative delta H reaction over T. We plug in our values for delta S the system, and for delta H, make sure that the units match in joules. Okay, so we have to convert kilojoules to joules there in order to get that to work. And then we solve for T, and it comes out that T must be greater than 1700 Kelvin. In order for this process to be spontaneous, T has to be greater than 1700 kelvins. That's a really high temperature, but it should make sense. The process's enthalpy is plus 22 kilojoules per mole. That means that you have to put heat into it to get it to go. So it's only going to work at a high temperature. Okay? So that's how we can determine what the temperature's effect on spontaneity might be. Here's another example. Methanol. Enthalpy of vaporization. So to go from liquid methanol to vapor, 71.8 kilojoules per mole. Entropy of vaporization, same process, the entropy is 213 joules per Kelvin. So both are positive. It's an endothermic process. Vaporization almost always is. And it is becoming less ordered or more disordered. So it's positive value for delta S. Okay, want to find the normal boiling point. Now remember what normal boiling point means. Normal boiling point means that that's the temperature at which we are in equilibrium, where the liquid and the gas are in equilibrium, because the pressure of the vapor pressure of the liquid is equal to the atmospheric pressure, and we're in equilibrium. Okay, so what do we know? Delta S of the system, 213 joules per Kelvin. Delta H is 71.8 kilojoules per mole. We'll have to change that. So that's 71,800 joules per mole Kelvin. So at the boiling point, vaporization begins to be spontaneous. Okay, so at the boiling point, delta S of the universe is 0 because we're at equilibrium. So that means that delta S system plus delta S surroundings must equal 0 because those two sum together equal delta S of the universe. Okay, so putting into our equation again, we have delta S of the system. We replace delta S surroundings with our negative delta H reaction over T. We're going to set that equal to 0. We plug in our values for delta S and for delta H. We solve for T. T is 337 kelvins or 64 degrees Celsius. That's our boiling point. That's the point at which, the temperature at which we'd be at equilibrium, which is what boiling point is. So spontaneity is a very important concept in looking at chemical processes or reactions, and entropy is like the central part of that right now. We will see that there is another component of spontaneity that we'll get into in a later video in this chapter. But right now, go back and make sure you understand how to determine the sign of entropy and how to use some of these calculations to figure out the temperature boundary, the temperature, either the temperature at which we're at equilibrium, boiling point or melting point, or the temperature at which you need to be above or below for the reaction to be spontaneous.